Hi, this is your video for Chapter 7, and in this chapter we're only going to cover sections 7.1 and 7.2. Section 7.1 is about properties of the normal distribution. The objectives in this section are 1. Identify continuous random variables. 2. State the properties of a normal probability distribution. 3. Explain the role of area in the normal density function. So the first objective is to identify continuous random variables. In the last chapter we talked about discrete random variables. So this chapter is all about continuous random variables. And a continuous random variable has infinitely many values. Those values can be associated with measurements on a continuous scale without gaps or interruptions. Here's some examples of things that would be continuous random variables. So if we had an experiment where we were going to measure the height of every student in a class, then the values of x, our continuous random variable, could be anything from 0 up to maybe 9 feet. Assuming that nobody in the world could be taller than 9 feet, so our values of x could be any value between 0 feet and 9 feet. Another experiment would be to record the amount of money spent on food and beverages by each fan in a sample of fans at a Colorado Avalanche game. So again, our values of x are going to be anything within a certain range. X couldn't be less than 0, so the values of x could be anything from $0 up. And the last example is to record the weights of passengers on an elevator. Again, our values are going to be in a range. This could be anything from 0 pounds up to whatever you assume the maximum weight of a person would be. So anything from 0 pounds up to maybe 1,000 pounds. But it could literally be anything in between those values. Continuous probability distributions are quite different than discrete probability distributions because, for one thing, they cannot be represented by a table that lists all the specific values of x and their probabilities. That works for discrete probability distributions because you can list those different values. However, for continuous probability distributions, we can't do that. So these are usually represented by formulas, which are called probability density functions. A density curve is the graph of a probability density function, and it must satisfy the following properties. First, the total area under the curve must equal 1. And second, every point on the curve must have a vertical height that is 0 or greater. That is, the curve can't fall below the x-axis. Because the total area under the density curve is equal to 1, there's a correspondence between area and probability. Objective 2 is to state the properties of a normal probability distribution. A normal probability distribution is a distribution for a continuous random variable with the probability density function shown here, where x is the continuous random variable, mu is the mean, and sigma is the standard deviation. Now the normal density curve is bell-shaped and symmetric about the mean mu. So here is the bell-shaped curve that we have looked at before. And this is what a normal density curve looks like. Here's our mean in the middle. The curve is bell-shaped and it's symmetric on either side of the mean. The total area underneath this curve is 1. And the area under the curve between any two values of x represents the probability that x is between those two values. It can also represent the proportion of the population for whom x is between the two values. Here's an example of normal distributions. Assume that men's weights are normally distributed with a mean of 191 pounds and a standard deviation of 30 pounds. Sketch the graph of the probability distribution for men's weights and interpret the graph. What does the area under the curve between x equals 131 and x equals 191 represent? So here is our basic bell-shaped curve, which represents a normal probability distribution. To draw the curve for this particular distribution, we're going to put the mean in the middle, so there's our 191. And then to show a little bit more what the distribution looks like, we can put some other values in here. So we're going to go down by one standard deviation at a time. So if we subtract 30 from our mean, we get 161. Subtracting another 30 gives us 131. And finally we have 101. So here we are 1, 2, and 3 standard deviations below the mean. Then if we go the other direction from the mean, we get 221, 251, and 281. So here we are 1, 2, and 3 standard deviations above the mean. Now the total area under this curve is equal to 1. And now for the answer to the other question, the area under the curve between x equals 131 and x equals 191. Well, let's shade this area in so that we can see what we're looking at. So if we're looking at between 131 and 191, it's very hard to draw straight lines with this computer, so I'm doing the best I can. There, we have the area shaded in between 131 and 191. So this area in here represents the probability that a randomly selected man weighs between 131 and 191 pounds, or we can also think of it as the proportion or the percentage of the population of males that weigh between 131 and 191 pounds. Now notice in this case, because our 131 is exactly 2 standard deviations below the mean, we could actually use the empirical rule to figure out what this proportion is. There is a relationship between the empirical rule that we used before and finding the proportion or the percentage of data values that are between certain values. There's a relationship between that and probabilities. Section 7.2 is about applications of the normal distribution. The objectives in this section are state the properties of a standard normal distribution, find and interpret the area under a normal curve, compute probabilities for normally distributed random variables, and find the value of a normal random variable. So first we're going to state the properties of a standard normal distribution. The standard normal distribution is a normal probability distribution with the mean mu equal to 0 and the standard deviation sigma equal to 1. The total area under its density curve is equal to 1. And again, that's true for any continuous probability distribution. So here's a picture of our standard normal distribution. And this is really just a special case of a normal distribution. It's just that it has a specific mean, which is 0, and a specific standard deviation, which is 1. And it actually corresponds to the z-scores that we talked about in Chapter 3. Because the values of the random variable here correspond to z-scores, we use the variable z instead of x when we're talking about the standard normal distribution. Here's an example with the standard normal distribution. For a standard normal distribution, what does the area under the curve for z greater than or equal to 1.5 represent? What does the remaining area under the curve represent? Here's our picture again. And if we put in the value of 1.5, And since we're talking about the area under the curve for z greater than or equal to 1.5, we're going to shade from here over to the right. And again, you're going to be shading in the same direction as your inequality points. So this area that we've got shaded represents, one, the probability that the z-score for a randomly selected member of the population is at least 1.5, or another way to think of it is it's the proportion of the population with z-scores of at least 1.5. The remaining area under the curve, in other words, the part over here that's not shaded, would represent the probability of the complement of the event z is greater than or equal to 1.5. So this part that's shaded is the probability for z greater than or equal to 1.5. The part that's not shaded would represent the probability of z less than 1.5. And remember, we said the total area under the curve had to equal 1. So if we knew the area of the shaded region, then we could find the area of the unshaded region by subtracting from 1. Our second objective is to find and interpret the area under a normal curve. So there are two methods for finding the area under a normal curve. One is using tables, and the other is using technology. Using tables is the old-fashioned, sort of old-school way to do it. And again, if you're using statistics in the real world, you would be using technology. So that's what we're going to do in this class. We are going to use either your graphing calculator or StatCrunch. And in this video, I'll be showing you how to use your TI-83 or 84. So to find areas or probabilities for a normal distribution, we will use the normal CDF function in your calculator. To find it, it's in the same menu as the binomial PDF and CDF functions were. So to find it, press second bars to get to your distribution menu. The normal CDF function is the second one in the list. And here you have to be very careful to use normal CDF, not normal PDF. The function will ask you for a lower bound for either z or x, an upper bound for z or x, the mean, and the standard deviation. And again, depending on what kind of calculator you have, you will either see normal CDF with the parentheses come up on your screen, or you will get a screen like this one. In either case, fill in the lower bound, the upper bound, the mean, and the standard deviation. Once you do that, you should end up with something like this on your screen. So here we have lower bound, upper bound, mean, and standard deviation. Press enter, and that will give you the calculated area or probability. Here's an example. We're going to find the area under the standard normal curve to the left of z is equal to 1.17. And one point about the variable z versus the variable x, if you see a problem like this and it gives the variable as z, that tells you right away that they're talking about a standard normal distribution. So you don't have to question what your mean or standard deviation are. The mean is always going to be 0, the standard deviation is always going to be 1. So first we want to draw a picture of our distribution, draw in the z-score, and shape the area of the picture. So here's our picture. We're going to draw in 1.17, and we're going to shade the area to the left of that, since that's what it said in the question. Now we're going to use the picture to figure out what our lower bound and upper bound for the z-values are. Another thing about normal distributions is that they don't actually stop. They continue on in each direction, so both to the left and to the right. So in a case like this, where we're just going from a value all the way to the left, we can't put negative infinity into our calculator, so we'll just put in a very large negative number. Again, since we don't really have a lower bound for z here as a number, we'll put in a very large negative number, such as negative 100,000. So here's what you would enter in your calculator. You would have normal CDF, negative 100,000 for your lower bound, 1.17 for your upper bound, 0 for the mean, and 1 for the standard deviation. If you put that in and press enter, you would get this value. So the area of the region that we've got shaded in here is 0.8790. And the standard for probabilities is that we round to 4 decimal places, so that's what I did here. Let's do a couple more examples. Now let's find the area under the standard normal curve to the right of z equals 1.17. So here again we've got 1.17, and I've shaded to the right of that. So this time our lower bound is going to be 1.17, and now we don't have an upper bound that's a number, so we're going to use a very large positive number, something like 100,000. If you put these values into your calculator, you will get an answer of 0.1210. And again, remember that the total area under this curve is equal to 1. So the area that we found in the last example was from 1.17 to the left. This one is actually the complement of that. So the answer that we got here is the same as 1 minus the answer we got in the previous problem. Now sometimes we do have both values. So now let's find the area under the standard normal curve between z equals 0.13 and z equals 1.35. So we would mark both of those on our picture, shade in between them. And this is pretty simple. We're going to use 0.13 for our lower bound, 1.35 for our upper bound. And again, since we're talking about a standard normal curve and we're talking about z, then we're going to use 0 for our mean and 1 for our standard deviation. So the area under the curve between 0.13 and 1.35 is 0.3598. Objective 3 is to compute probabilities for normally distributed random variables. So far we have only worked with the standard normal distribution, which has a mean of 0 and a standard deviation of 1. And the variable we use to represent values in this distribution is z. But there are many other types of normal distributions that are not standard. That is, the mean is not 0, or the standard deviation is not 1, or, most of the time, both. For these normal distributions, we usually use the variable x to represent the values. Remember still that the area under a normal curve represents a probability. So here's an example of finding probabilities for normal distributions. Maximum capacities for elevators are determined by the maximum weight that the elevator can hold, and the maximum number of passengers is determined by assumptions about average weights. Suppose the maximum capacity for an elevator is found to be 3,500 pounds, and the maximum number of passengers is given as 25. This assumes that the mean weight of the passengers is 140 pounds. Assume the worst case, that all passengers are men, since men have a greater mean weight. Assume also that the weights of the men are normally distributed with a mean of 191 pounds and a standard deviation of 30 pounds. So if one man is randomly selected, what is the probability he weighs less than 140 pounds? So we want the probability that the weight x is less than 140. In probability notation, this would be probability x less than 140. Again, we're going to draw the picture of our distribution. And when you do this, it's a really good idea to label the mean and then at least one standard deviation below and above the mean, just so you get a general idea of what the distribution looks like. So 191 was our mean, and if we go one standard deviation below and 1 standard deviation above that, we've got 161 and 221. Now our 140 is a little bit below 161. So we want the probability that x is less than 140, which means that we're going from 140 to the left. Again, we can look at which direction this inequality points to tell us which direction to shade. So again, we don't have a bound on the left end, so we're going to use a large negative number like 100,000 for our lower bound. We'll use 140 for our upper bound. And this time we're putting in 191 for the mean and 30 for the standard deviation. So if you put that into your calculator, you should get an answer of approximately 0.0446. Now this probability is less than 0.05, so we would actually consider this to be an unusual event. And I would think in this case that the elevator company might want to reconsider some of their assumptions, and they might want to change what their maximum number of passengers would be. Here's another example. If we look at IQ scores, they're also normally distributed with a mean of 100 and a standard deviation of 15. So first of all, we can figure out what percentage of the population has IQ scores at or below 90. So first we're going to draw our picture, and again I'm labeling the mean and 1 standard deviation below and 1 standard deviation above. You can label more than this, but for sure you need to have at least these 3 values labeled. Then the value we're interested in is 90, and because we're going from 90 down, that means we're going to shade from there to the left. And if we want to write this in probability notation, this would be the probability that x is less than or equal to 90. Again, the inequality is pointing to the left, just like our shading is going to the left. To put this in your calculator, again we'd use a large negative number for our lower bound, we'd use 90 for our upper bound, and our mean was 100, our standard deviation was 15. On your calculator, this should come out to be about 2.2525. That means that about 25% of the population has IQ scores at or below 90. If you remember when we talked about percentiles back in Chapter 3, this could also be interpreted as the 25th percentile for IQ scores, because about 25% of the population has a score of 90 or lower. So part B of this problem says, what is the probability that a randomly selected person has an IQ score above 90? Now this time we're going to use the complement to figure this out. Since we just found the probability that x is less than or equal to 90, x greater than 90 is the complement of that. So all we would have to do is subtract our previous answer from 1. Our previous answer was 0.2525, so if we subtract that from 1, we get 0.7475. Part C asks, what is the probability that a randomly selected person has an IQ score between 85 and 115? So here's our picture with our 3 values labeled, and it just so happens that 85 is exactly 1 standard deviation below the mean, and 115 is 1 standard deviation above the mean. So here's our area shaded in between those two. So for this we can just use 85 as our lower bound and 115 as our upper bound on our calculator, and we put in the 100 for the mean and the 15 for the standard deviation. And this gives us an answer of 0.6827. If this seems somewhat familiar, that's good. When we talked about the empirical rule back in Chapter 3, remember that said that approximately 68% of values are within one standard deviation of the mean. And that was when we had a bell-shaped curve. So that ties directly to what we have here. We've got exactly one standard deviation below and one standard deviation above the mean, and the area under our curve is the same as the percentage of data values that would be between those two values. Objective 4 is to find the value of a normal random variable. And what this means is that if we're given the area under the curve or the probability, then we can work backwards to find the value of the variable. In order to do this, we have to know the mean and the standard deviation of the normal distribution. And on your calculator, the function inverse norm, which takes the probability, the mean, and the standard deviation, finds this value of x for us. The function assumes that the area under the curve is to the left of the x value. Here are some examples. First, we'll find the cutoff value for z-scores so that the area to the left of z is 0.81. So again, we're going to draw our normal distribution first, and this time we have to make an educated guess about where our cutoff value is. And you can think about the empirical rule when you're doing this. The important part here is that if our area is 0.81, that's bigger than 0.5, which means that our area has to cover more than half of the graph. Remember, this is symmetric on either side of the mean, which is at 0 here. So since we're going to the left of z, we want this to be above the mean so that the left of that will include more than half of our graph. So I just made a guess about where the z might be, shaded from there to the left. So the idea is that this is the value we're trying to find, what value of z this is. Our area under here is the 0.81. So we would use the inverse norm function on the calculator, and here we put in the probability or the area, the standard deviation, and the mean and the standard deviation. If you put this in your calculator, you should get back an answer of 0.88. So that means that this value of z right here would be 0.88. Second part of this problem is to find the cutoff value so that the area to the right of z is 0.4677. So again, we're going to draw our distribution and make kind of an educated guess about where our cutoff value might be. Since 0.4677 is close to 0.5, that means that we should have almost half of our graph. And we're going from z to the right this time, so we want to put this just a little above 0 so that this is not quite half of our graph. Now, because of the way the inverse norm function works, it won't tell us the value if we're going to the right. So if we have a situation like this, we have to figure out what the unshaded portion of the area is in order to use our inverse norm function. So we have 0.4677 on this side for the area. That means on this side we have 1 minus that, which is 0.5323. So that's the value we would put in our function with our mean and our standard deviation. And if we do that, we would get z equals 0.08. So in other words, the value right here, that's our cutoff value, is 0.08, just barely above 0. Another example, going back to the elevator example, we're assuming that the weights of men are normally distributed with a mean of 191 pounds and a standard deviation of 30 pounds. What weight separates the lightest 10% of men from the heaviest 90%? This is another way of asking for a cutoff value. We're looking for the boundary value that separates the lowest 10% from the highest 90%. If you think about that in terms of where the values are, this means that we're looking for the area to the left of the value to be the 10%. So if we draw our picture, and again I put in the mean and one standard deviation below and one standard deviation above, we can make an educated guess about where that cutoff value might be. And it's not that important that you're totally accurate on these, as long as you realize that 10% is going to be less than half of the graph, and as long as you're shading in the right direction. That's the important thing. So again, I just made a guess about where this value might be, shaded it to the left. So this area in here is our 10%. The area over here would be the 90%, but we can't use that if we're using that function on our calculator, because it will calculate from our cutoff value to the left. So we're going to use inverse norm 0.10, 191, 30 to get our cutoff value, which turns out to be 152.6. So the value right here is 152.6 pounds. So that would be the cutoff for determining the lightest 10% of men. So in other words, men who weigh less than this would be in the bottom 10%. Men who weigh more than this would be in the top 90% as far as weights. We could also interpret this as the 10th percentile for men's weights.